Hi class, welcome to the first section of chapter 5. Here we move away from what we've been doing before, which is differential calculus, and we move into integral calculus. So calculus 1 focuses on derivatives, calculus 2 focuses on integrals, and calculus 3 is derivatives and integrals in 3 dimensions. So this is our precursor to integral calculus, where we start to work out the foundations of calculus 2. Okay, so really what we're focusing on today is area and distance. Okay, a lot of times what we want to do in a calculus 2 level course is we want to find the area under a curve. Okay, so our curve is given by a function f of x. A lot of times we want to know what is the area below the curve and the x-axis, right? So this is a very, very important concept in calculus. We'll see how it ties in together with what we've been doing so far in this calculus 1 course. But it's a very, very important thing. It has a very strong foundation in calculus, okay? So this leads to what is called integral calculus. So again, as I said before, so far we've been doing differential calculus, and so we're working our way towards the basics now of integral calculus. Okay, so right, so up to this point we've been doing differential calculus. So this chapter focuses on the fundamentals, right, on the basics, on the foundation that we're going to need in order to get it started into calculus 2 style materials. Okay, when we say the area under a curve, we mean the area between our function and the x-axis, right? So generally we mean above the x-axis and below our curve. However, if the values of our curve are negative, well, then that means it needs to be the values that are above our curve and below the x-axis, right? So basically any area between our curve and the x-axis is what we're looking at. So a lot of times we're only interested in the area from one point to another, right? A starting point to an end point. There are definitely times when we're interested in the area below a curve for the entirety of the curve. But generally we are interested from one point to another, especially for calculus 2 style material. Okay. So for instance, if I have my curve, okay, which is given here, which I can call f of x, as you can see, at least for the snippet that we're looking at, it's parabolic in nature. It looks like a parabola. Although I don't know what it does out here. It could, hit several local max and mins. This could be something larger than a parabola, but for the part that we're looking at, it's just a parabola, which is not important to us right now anyways. Okay, so we know that this is the x-axis, this is the y-axis, and this is my curve. So the area between my curve and the x-axis is all of the material under my function. Now, as I said before, we're generally interested in a starting point to an ending point. Generally, our starting point we call A, and our ending point we call B, right? So from A to B, the area under my curve is this given shaded region. Okay. Now, finding this area can be very, very difficult sometimes. When my function is a nice function and it takes on a nice standard geometric shape, it's very, very easy to find the area under this curve, right? So for instance, if f of x was a straight line, well, this area would be a trapezoid, right? Which I could find by using the formula for the area of a trapezoid, or breaking this down into a rectangle and a triangle and finding that area, okay? But for regular functions, it's generally not that simple, right? A standard curve. Now, obviously, I could try to make a trapezoid out of this and get a pretty good approximation for the area with the information we know now. But what if my curve has several ups and downs, or has several local maxes and mins in between A and B? What if it's not so nice like this, right? So that's kind of what we're going to discuss for this section 5.1, is how to figure out the area under this curve. Okay. So again, a curve is continually changing, right? It is not a straight line from here to here. It is a curve. So at any one point, it's changing at some rate, which is given to us by a derivative, right? What is its current rate of change at whatever point I'm interested in? But over the life of the curve, it's changing continuously, right? So it's very hard to find the area below because it's not a straight line, for instance. Again, right? I can't find a geometric shape to fit this. This one I can to an extent, but maybe I couldn't for a different curve. Okay, for instance, let's say that this was my curve. It's very, very difficult for me to find a single shape that would approximate the area under this curve, either for the life of this function or from some endpoint, say negative 2.75, right? Up to, let's say, negative 1, so that we're, in between a good starting point and ending point so that we can kind of see what's going on. So this is what the area under the curve is. So for my example that I had on the PDF that we're looking at, it was easy to find a nice simple shape, right? So for instance, if I had this to negative 2.5, okay? It's easy to kind of make, like I said before, a trapezoid to approximate this, right? But when we're over the life of our function and our function is doing interesting things over the interval that we're interested in, I can't have a single shape, right? And I don't want to just say, oh, well, from here to here, I'll draw one kind of graph, and from here to here, I'll draw a different trapezoid, and here to here, a different trapezoid, because we can really only do that if we know what our function looks like. Okay, a lot of times we don't graph our function, we don't spend the time to analyze it that deeply to say, oh, from here to here, this is the kind of shape that I would like to use, right? We need a more systematically universal approach to this, right? I know in Calculus 1, a lot of what we do is say, okay, let's analyze this function, right? Like, what's the largest points, absolute maxes, absolute mins, local max and mins, when is it increasing, when is it decreasing, inflection points. We do all of these things, right? And we could use that approach to try to guess the area from one point to another, but we would have to do that curve sketching that we do, that function analysis for every function every time you want to do this. So we have a better approach of doing that, which is what we're going to talk about throughout this chapter, chapter 5, that's a little bit more systematic than taking our function, either graphing it by hand or analyzing it through Calculus 1 differential methods, and then trying to make shapes that approximate our, our pieces under the curve up to a point. Okay. As I said, when our shape is simple, we can use a simple shape to try to approximate this, but again, that's generally not what's going to happen. This is just a very simplified diagram to show you what we're kind of trying to do here, right? So again, the easier way to do this is just to use the most basic shape that we learned from elementary school, which is a rectangle, right? Because even trapezoids can be kind of difficult for people, especially if I need to break this down into several trapezoids. So something easier is to break it down into rectangles, okay? So I will approximate my curve using a single rectangle. Now, as you can see, the height of this rectangle, for me, can vary. Like, how do I know how large to make it? It makes sense here for me to make it this high because my highest point in my function is on this side. But we call this a right-hand approximation because I'm using the right-hand endpoint to make the height of my rectangle. I could have easily used this as the height of my rectangle. So then my rectangle would be smaller than the area under the curve, but it wouldn't matter too much because this is an over approximation. The area is larger for this rectangle than it is for the area under the curve. If I used this point as the height, then it would be an under approximation because the area of my rectangle I'm using is smaller than the actual area under the curve, right? So we actually use both. There's times when there's not really a time where one is better than the other, but it's important to make that distinction at this point that we can use the right hand side of our rectangle as the height, or we can use the left hand side of my rectangle to make the height of my rectangle. Okay, so again, this is obviously not a very good approximation, but the reason we use rectangles instead of trapezoids is because rectangles are easy to use. It's easy to find the area of a rectangle. base times height, right? This distance times this distance. Super easy. If I use a trapezoid, it's not as easy because I have to find my base. I have to find my height, right? And I have to have my approximating line between one point and another point. So that the formula for rectangle is 1/2 times the height times base 1 times base 2. So this would be base 1, this would be base 2, and this would be my height, and I divide it in half, right? Which actually pops up later in calculus 2 somewhere else. But for right now, we're going to keep it as simple as possible and use rectangles, okay? So, as we see here, one rectangle doesn't give a good approximation, right? If I use the left side as the height, it's not a good approximation either. So something better to do is, over the life of A to B, instead of using one rectangle, let's use two rectangles, okay? So as you can see, it's still an over approximation, but it's much better than what I had here, right? Here I had a very large piece of area that was larger than the area under my curve. If I break it down into two rectangles instead of one, I have a whole chunk here that's no longer being taken into account. So my area is much more accurate compared to this one. Okay, so here I have a huge shaded area that's more than what I want. Here, I still have more than I need by using two rectangles, but it's not as much as when I had one single large rectangle. Okay, it's a much better approximation. In fact, the more rectangles I use, the better my approximation is going to be. Okay, so generally what we're going to do is we're going to approximate our curve using n rectangles, okay, where n is either given to us or we make it as large as we want it to be, basically. Okay, so again, so compared to one, I now have two rectangles. And again, notice that both of my rectangles are using the right hand side, right, the right side edge to form the height, right? This is the right side edge of this rectangle, right? Its right side edge is the height. Okay, so this is what it looks like if I use one rectangle to approximate my curve. If I use two rectangles over A to B, right, so their lengths are the same, right? So I just cut it in half, basically. Okay, so you can see the difference in the approximation. Here, if I'm using n equals 4, so each of these rectangles I cut in half. So now I have 4 equal sized rectangles. You could see that the approximating area is a lot closer, especially compared to 1, right? This is a large overestimate. This is much, much closer to what we would expect the actual value to be. And if we cut each of these in half to give us n equals 8, look how much closer now this approximates my area compared to 1, right? So increasing the number of rectangles I use gives me a better and better approximation. So as n approaches infinity, as the number of rectangles we use gets larger and larger, right, we approach the exact area under the curve and we minimize our error, right? So again, as n gets larger, okay, the approximation becomes closer and closer to the true approximation. And in fact, when n equals infinity, we have the actual area under our curve, right? If this was an infinite number of rectangles, well, that's what happens when you have your points along your function, right? There's an infinite number of points from A to B for the outputs of my function. So there's an infinite number of rectangles, right? If I think about if I had to color this in, what would you do? You would color it in up and down by drawing straight lines until you're here, right? That's basically what this is. Each rectangle is infinitely thin, right? And so it's just an infinite number of lines to color this in. There's an infinite number of rectangles here under my curve from A to B, right? So as I make, okay, so that's why if I only have one rectangle, it's not a good approximation. But when I have more, it looks better. And if I had an infinite number, there would be no over approximations. There'd be no over areas because each line would be the height of an infinitely thin rectangle, right? A rectangle with a width of 0, basically. Okay. So for every approximation we've done so far, as I said before, we were using the right-hand side, right, of the rectangle to find the height. Okay, the right side of the rectangle. Okay, this is the left side. It is not on my function. The right side is at my function value, right? If I plug b into my function, this is the point I get out. That's the height of my rectangle. Okay, same thing here. For this middle point right here, if I plug it into my function, that's what I get. That's the height of this rectangle, right? So I'm using the right-hand side in order to form my rectangle, so we call it a right-hand approximation. Okay, and that's because, again, our rectangle is the same height as our curve on the right side of the triangle. Okay, on the right side of the triangle, it's as tall as my curve. Right. So in this case, our approximation is an overestimate because the area that we get out from our approximation is larger than the actual area of this that's under the curve. Right. We can use left-hand approximations as well. As I said before, it works the same way. The height of my curve, or the height of my rectangle, I'm sorry, is based on the left-hand side instead of the right-hand side. Okay. So when my curve is concave up, like in our example, a right-hand approximation will be an overestimate, and the left-hand approximation will be an underestimate. Okay. If my function is concave down and increasing, so here it would be still increasing but concave down, just think about how that would be different, right? A right-hand side approximation then would be an overestimate still, and the left-hand side would still be an underestimate. Okay, a right-hand approximation would be an underestimate. So when our curve is concave down and increasing, the right-hand approximation will be an overestimate, and the underestimate will be when our curve is concave down and decreasing. So depending on the concavity and whether the function is increasing or decreasing over our interval a and b, will determine whether or not a right-hand side is an over approximation or under approximation, and same with the left-hand side. The left-hand side can be an over an approximation, and it can be an under approximation. It just depends on the concavity and whether the function is increasing or decreasing over that interval. And again, that's also why we don't use the trapezoid approximation, because you'd have to really analyze your curve in order to get the best approximation. Okay. Now, again, I want to put an asterisk on that because we do have what's called the trapezoid rule for this, which is very accurate. But we're not going to get into the particulars of this, and we can do it without analyzing our curve. Okay. So for our previous example, the left-hand approximation would look like this. Okay, so same curve, it's concave up and increasing. The light gray is the area under my curve. The dark gray is our left-hand estimate. So you can see when n equals 1, I have a rectangle that's a lot smaller than the full area under the curve, right? So the dark gray is the left-hand approximation. Okay, here I have n equals 2. So I cut this in half, so that gives me two rectangles. Again, the left-hand side of the rectangle is the same height as the function. So that's how I determine how tall my rectangle is. Okay, so as you can see, when n equals 2, it's a much better approximation. It almost covers all of the area a lot better than when I just have one small triangle, right? When I double the number of rectangles, it's a much better approximation. There's much less area that's not covered compared to 1 and compared to 2. And then when I cut all of these in half and use n equals 8, as you can see, that's a very good approximation as well, right? So whether it's a left-hand side or a right-hand side approximation, a larger number of rectangles gives you a much better approximation, right? So this is very accurate, as was n equals 8 for an overestimate. So depending on the concavity, you're either going to get an overestimate or an underestimate, and depending on whether your function is increasing or decreasing as well. Okay. So this brings us to our discussion of what are called Riemann sums. So Riemann sums are something you should have covered in a pre-calc course. I know at my campus sometimes they're not always covered. I generally cover them in my classes. At the moment, I do not have a Riemann sum video available. We're going to go over it right now, but I should have something up in the future if this is being watched later on, you know, a year or so from now by somebody else. Okay. So Riemann sums come from what are called series. Okay. So a series is basically just a sequence of values that are being added together. They generally follow some sort of pattern. There's a lot that has to go into Riemann sums. In fact, in Calculus 2, they're a very, very large part of study for a standard Calculus 2 course towards the end of a Calculus 2 class. Okay, we're not going to get that deep into it now. Obviously, this is still just a Calc 1 class, but we do need them in order to flesh out the idea for finding the area under a curve. Okay, so basically what we're doing is we're adding a bunch of values together. These values follow a pattern. Okay, that sum is called a Riemann sum, right? The notation for a Riemann sum is the following. Okay, so we call this sigma notation because this is the Greek letter sigma. Each of the things here are important to us. Okay, so we'll go ahead and just lay out what each of these things mean, and you should have an idea already. K is what's called our index counter. It's what is keeping us on track. K is a whole number, a positive whole number. It starts from whatever value I have for C. Okay, I could start C at 0. I could start C at 1. I can actually start it in the negative values as well. Generally, we start at 0 or 1. I could start it at 10 if I want to. Okay, it doesn't really matter. K is your counter. C is the number that you start at. K goes up by 1 each time. So if C is 1, I then go 1, 2, 3, 4, 5, 6 for K. K counts up by 1 each time. Okay. N is my ending index. It's where I want to end at. So if I want to start at 1 and I need to add up to a fifth term, C will be 1, N will be 5, and K will count starting at 1 and end at 5. It'll go 1, 2, 3, 4, 5. A of K is the terms that we add together. They generally follow some sort of formula. K will be the index that I'm counting, you know, as when K is 1. For the first term, everywhere I see K, I plug in 1. For the next term, K bumps up to 2. Everywhere I see K, I plug in the value 2, and I'll add those two things together. And then 3, and then 4, and then 5, and then 6, all the way up until N. Okay. So let's just do an example, in case you've never seen that before. Let's say that this is my Riemann sum. K is going to start at 0. I'm going to go up to 4, so that's actually 5 terms, right? That's the 0 term, the 1 term, 2, 3, and 4. So that's actually 5 terms. Each time, I'm going to plug in 0 for K, and then 1 for K, and then 2 for K, and then 3 for K, and 4 for K, until my ending index, which in this case is 4, and I add all of those things together. Okay, so in order to expand this Riemann sum, I start with the 0 term, which will be 2 to the 0 minus 0. Then I am now at my first term, so I'm going to plug in 1 everywhere and add that to my 0 term. So it'll be 2 to the first power minus 1. Now I'm on the second term, right? My counter is counting up. So 0, and then 1, and then 2, and then 3, and then 4. And I end here because my Riemann sum tells me to end at 4. So it's really pretty straightforward. K is what's kind of changing over time. This is what my formula looks like. So my A to the K term is this 2K minus K. So this is what my formula looks like. Each time I evaluate on my counter, I'm plugging in my counter value, right? So my counter was 1, my counter was 0, my counter was 1, my counter was 2, my counter was 3, my counter was 4, until I'm done. And then I would add these all up. Obviously, I don't want to keep it this way. I would actually add these values up, which I do for this example. So this is 1, this is 2 minus 1 is 1, this is 4 minus 2 is 2, this is 8 minus 3 is 5, 16 minus 4 is 12. So it's really 1 plus 1 plus 2 plus 5 plus 12, which is a value of 21. So my Riemann sum here is actually 21. Now what we're going to, this is actually what we're going to do. Okay, so in Calculus 2, when you approach these, you don't actually have values to plug in. A lot of time we actually look at these as n is infinity, right? So there's an infinite number, so you can't really just be plugging in values and add them up. Okay, there is ways to do that depending on what your Riemann sum looks like. But that's what a Riemann sum is, right? Notation wise, this is what its parts do, and here is an example of that. Okay, so hopefully this is not the first time you've seen this. Hopefully you've seen this in your pre-calc before, because you will cover this in Calculus 2 in great depth, right? So one thing to notice about what series, these are called the series, right? A Riemann sum, is that you can get the exact same thing out by changing your index. Okay, so for instance, I could change my k here to start at 1, and if I change the way that my my summation formula works, I'll get the exact same things out. Okay, so for instance, if I start this at 1 and I make this k minus 1 and this k minus 1, I get the exact same thing out. What happens when I plug in 1? I get 2 to the 0. 1 minus 1 is 0, right? So if I start at 1 and I change my inside function to look like this, I get the same thing out, right? When I plug in 2, I get 2 to the 2 minus 1, or 2 to the 1, minus 2 minus 1, right? So I get the exact same formula out by manipulating my starting value for my counter and manipulating the function inside of my Riemann sum. Okay. So that's our quick and dirty introduction into Riemann sums. So combining everything that we have together so far, right, which is this idea of Riemann sums that we've talked about, and finding multiple rectangles under a curve in order to approximate its area, we're gonna form Riemann sums with these rectangles, right? So we're gonna create n approximating rectangles. We would prefer them to have equal sized bases, right? So it's completely possible that I chop things up under my function in a way so that, you know, it correlates with whatever's happening to my function, like I said before, looking at the local max and mins and all that kind of stuff, right? Like this. Okay, so for instance, if this was what my curve looked like, I'd have to find all of the local max and mins along my interval from A to B, and then I'd have to try to form trapezoids basically to approximate across those. If I was to not use rectangles, for instance, and I wanted to do it, you know, minimal as possible, it's actually a lot more work to do that because I have to take my function, find its first derivatives and its critical points for its derivatives, and then I have to evaluate. It's a lot of work. Obviously, as you see, these bottom spaces here are not equally defined, right? They're not equal distance apart. They have weird values, so it's nicer if I can just do this with rectangles that are all uniform, because then I can use a very simplified formula in order to do this, which is why we're using rectangles, and I want their bases to be uniform in length. So as we create our n approximate rectangles, we'd want them to have equal sized bases because it's easier that way. I have just kind of one formula to stick with. I don't have to do a lot of extra exploration and analysis using derivatives and critical points and things like that, right? So the size of each base is going to be my complete distance, right, from A to B divided into n equal pieces, right? So that should make sense. From A to B, and I divide this into 8 equal pieces, right? From A to B, I divide this into 2 equal pieces. A to B into 4 equal pieces. that's the size of the base of any one of these rectangles. They all have the same size. I took their length, divided into 4 equal pieces, or 8 equal pieces, or 2 equal pieces, or even 1 equal piece, right? So that's how that formula works as far as the base of my rectangle, right? B minus A, the complete distance I'm interested in, divided into equal sizes of the number of rectangles that I want. Okay, so this is the length between each x value that I'm going to use for my inputs into my function, right? Because remember, the height of my rectangle is my function evaluated either on the right side or on the left side of this length, right? To get the height of the rectangle. Okay, so what we call this is delta x, because again, this is a length from one x value to the next. So delta x, my change in x from one to the next, is b minus a over n. Okay, so if this is in 8 pieces, from one to the other is the length of the change of x. Okay, so each of these bases has a length of delta x, or b minus a divided by n, right? My change in x. So we now have n plus 1 x values of interest to us, right? So again, I've cut this into 8 pieces, right? So I have 1, 2, 3, 4, 5, 6, 7, 8 endpoints plus the one I start with, right? So if I divide this into 8 intervals, there's actually 9 points of x, okay? So what does that look like to us? X naught is my initial value of a. X1 is my previous value plus a distance of delta x. My previous value plus the length of the base of my rectangle, right? That's how I get to the next value of x, right? X2 is the same thing. It's my previous x value plus my change in x to get to the next width for my rectangle, so forth and so forth until the ith x value looks like this, the previous x value plus delta x. And I go all the way until I'm 1 away. So I'm looking at the second away plus the delta x. This should be a plus, I'm sorry about that. And then my last value is b, right? Or x, the value right before b plus the delta x, right? If we form a right-hand sum, I'm always using the left side piece. So I'm not going to use x naught, but I'll use all of the other terms, right? So we call that a RHS, a right-hand sum, because the heights of my rectangle are given by the right side, okay? So we call this a right-hand sum approximation for our curve. Our rectangles have a height of f of x1, right? So I don't use x naught for my height. Okay, so if a is x naught, that's not the height. It's the next one. Okay, the next one is the height of my rectangle. So I don't use the first point, but all the points after that. That's how I get a right-hand approximation. Let's come back here a little bit. Those are left-hand approximations, right? So right-hand approximations, I'm using not the first one to give my height, but the next one. So if this is x naught, this would be x1, this would be x2, right? Or in this case, xn. So I'm using not the first one, but the next one. The second point is the height, and then so forth and so forth. And that's for a right-hand sum. Okay. So for right-hand sum, I'm using f of x1, f of x2, so forth and so forth until f of the endpoint, f of xn, or in our case, f of b. Okay, it's the same thing as xn, the last term. I do not use the first point, but I use all of the other points in order to get the height of my rectangle, right? So I plug that x value into my function. That's how I know how tall my rectangle is. For left-hand sum, it's the same thing, except we start with the first point and we don't use the last point. under approximation, I use the first point, but the last point doesn't get used. I don't use this one, right? I'm only using the first point. I use the first point, I use the second point, but not the last point, because that's the right-hand side of the last triangle. So I use the first one, I use the second one, the third one, the fourth one, but I don't use this last value. It doesn't get used. Okay. So for left-hand sum, you use all of the values except for the last value. Okay. Oops. All of the values starting from the first one to 1 minus 1 before the last value. For a right-hand sum, you don't use the first one, but you use all the ones after that. So that's the difference between a left-hand sum and a right-hand sum. Okay. The ith rectangle in a right-hand sum has an area of f of xi delta x. Okay. And the ith rectangle in the left-hand sum has an area of f of xi minus 1 delta x. So in the ith triangle, the ith rectangle, xi gives the right-hand side and xi minus 1 is the left-hand side. So in the ith rectangle, this could be the third, right? If this was the third rectangle, you would use x3. If this was a third rectangle in the left-hand side, you would use x2. That's basically it, right? Whichever rectangle you're interested in, the ith one, right-hand side, you use the ith value of x. For a left-hand sum, you use one less than the rectangle you're interested in. That's all that this means, okay? The ith term, we use this a lot. That just means any generic one that we're interested in, whether it's in the beginning, at the end, in the middle, anywhere. It doesn't matter. It could be the first one, it could be the last one, it could be right smack dab in the middle, it could be 3/4 of the way in. It doesn't matter. It's just a way for us to keep track of what these look like in general. Okay, so this is what we have so far, right? So we've been building this up piece by piece. I have my interval from A to B. I'm using n rectangles. I know that there's 8 here, but that's only so we can kind of see what's going on. If I'm interested in the ith rectangle, okay, so this is just some generic rectangle. It doesn't mean it's actually the 5th one. It's the ith one, right? Whichever number that is. The right endpoint is given by xi. The left endpoint is given by xi minus 1, right? So this would be the 5th x value, the 4th x value if we were actually counting. The distance between this, the base length, is delta x, and the height, using the right-hand sum, is f of xi. If I was using a left-hand sum, its height for this rectangle would be given by f of xi minus 1, right? So any one of these rectangles has a base of delta x and a height of f of xi, where xi in this case is the right hand side. If I want to do left hand side, I would plug in the other side instead, right? So that's what this is. Each of these rectangles looks like this. And so basically, since they're all uniform, except for their heights, I have a generic formula I can use then to add these up, right? Because I want to find the area of this rectangle and this rectangle and this rectangle and this one 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 and this one, and add them all together, right? So our right-hand sum then has a form of the given, right? So the area under this curve from A to B is approximately given to us by f of x1 times delta x, because I'm not using the first one, right-hand side, so I'm not using x0, I have to use x1. The base is delta x, so height times width, right? Height times width, plus so forth and so forth until I can add up the middle one, right? Because this is just a generic form, that's why we keep the ith term in there, all the way until the last one, right? So the first one looks like this, the second one looks like this, the generic term looks like this, all the way until the last one. And in the right-hand sum, we do actually use the last term. B is xn, right? So I evaluate B at its height, multiply it times its width. That's our approximation for the area, right? I broke it up into equal-sized rectangles with differing heights. The height is based on the curve, and then I add all those together. So it has a very standard form here, right? I'm adding up a bunch of function inputs times delta x. So if I pull out delta x, you can see here I'm left with a sum. I had a sum before as well, but I had a common factor of delta x. That was common everywhere. So I can pull that out. I know delta x is the same as b minus a over n, right? So if I'm starting to put this into the form of what it would look like for things that I would plug in, b minus a over n times, plug this point into my function, plug this point into my function, plug this point into my function, and add them all up, right? The shorthand notation for this is the Riemann sum from k equals 1, up to n, okay, of f of x to the k. Okay, so it's a Riemann sum. So I could take this long expression I have here, which can be very long sometimes, and break it down into a very short formula that looks like this. Okay. Most of the time when you see this, you'll have the same Riemann sum, and we'll just keep the delta x right here in front. Okay, but here I'm trying to show you that this delta x is the same as b minus a over n. Okay, so that's my Riemann sum for a right hand. Okay, so generally we would write this like this. As I said before, we would keep the delta x not as b minus a over n, but as delta x, and we would just keep it attached here because this is my area, right? My height times my width, and I'm summing up all of them to get that area under the curve. If I want to do a left-hand sum, I would start at k equals 0. I can keep the same index, but because remember, I'm starting at the 0 term, right? The first one at a, not at the next one up, and I end one before the end because the last term, the nth term, is on the right side of the last rectangle. The n minus 1 term is on the left-hand side of the last triangle. So I can just keep it like this. So the formula looks the same. I just have to change my indices, so I'm starting and ending one x value earlier than I do with my right-hand sum. Okay, so as n goes to infinity, as we said before, our approximation here becomes the actual area under the curve. So the area under my curve from a to b, okay, is given by the limit as n goes to infinity of my right-hand sum notation. I can also do it for the left-hand sum notation. It doesn't really matter which one I use. Because we saw that one is an over approximation, one is an under, right? But as I go to infinity, they both go to the same thing. Okay, so that's why I have two different formulas here, because I can either use the right hand or the left hand, but as n goes to infinity, they're the same thing. That's going to equal the area under the curve. So as I choose very, very large values of n, as I let n go to infinity, I'm going to get the area under the curve. Okay. So why is this important? Okay, so the area under the curve tells us the distance traveled from point A to point B if my function is a velocity function. That's one of the uses that we use for this. Just like for derivatives, if I have a position function, the derivative tells us the velocity function. If we already have a velocity function, the area under the curve tells us how far we've traveled. Okay. So example, I want to estimate the area under the curve, f of x equals 3 sine of x over the interval x equals 0 to x equals pi. I'm going to do this with a right-hand sum with n equals 4. So I'm going to take this curve here, and I'm just going to break it up into 4 equal parts, and I am going to use a right-hand sum because that's when we've been doing the most. So I'll just kind of stick with that, and we'll form a right-hand sum. So we're going from 0 to pi here. Okay. So my delta x is pi minus 0 over 4, right? B minus a over n. So each of my bases has a length of pi over 4. Okay. So that means that we're going to start at 0, and all of the x values of interest to us, again, are going to have a length of pi over 4. So we're really just going to count by pi over 4s. So the first one will be 0. Our next x value of interest is pi over 4, then pi over 2, then 3 pi over 4, and then pi, right? So that's the breakdown of the interval that we want. We break it into 4 equal parts. each of those parts a length of pi over 4, right? So x0 is 0, but I'm doing a right-hand sum, so I don't need x equals 0. I need x equals 1 first. So my 5 intervals, my 5 values are 0, x1 of pi over 4, x2 is pi over 2, 3 pi over 4, and pi. Okay, but again, for a right-hand sum, I don't need x0. I don't need x0 equals 0 because that gives me the left-hand side of the first rectangle, and I don't need that for a right-hand sum. So these are the x values that I need. Okay, so my delta x I know already, it's pi over 4. I need to plug these values in to my function to get the function heights. This is the height of the first rectangle. When I plug this into f of this is the height of the second triangle, f of this is the height of the third rectangle, and f of pi is the height of the fourth rectangle. Okay, so plugging it into this sum, okay, I know what delta x is, I know what my different xk's are, starting with k equals 1. Okay, x of 1 is pi over 4, delta x is pi over 4. x2, okay, k being 2, is pi over 2, delta x is pi over 4. F of 3 pi over 4 times pi over 4, and then the last one is f of pi times pi over 4. Okay, that's my sum. Once I find all these things out, I'll have my approximation. So I can pull out pi over 4 because you can see that's a common term. So instead of multiplying these each time, it'll be easier just to pull it out and add up the sum of my function values, right? So 3 of sine pi over 4 plus 3 sine pi over 2 plus 3 sine 2 pi over 4, or I'm sorry, this should be 3 pi over 4. It's me writing too fast. And 3 sine of pi. Okay, so if I plug all those in, I'll get pi over 4 times 3 root 2 over 2. That's what we get for sine pi over 4. Pi over 2 gives me 1 for sine, times the 3. Sine of 3 pi over 4 is root 2 over 2. And sine of pi is 0. Okay, so if I add all these up, again, I can pull out this common 3 that's here because it's 3 sine everywhere. I have 3 pi over 4, pi over 2 plus pi over 2 plus 1, right? So that's pretty easy. That gives me basically 3 pi over 4, 1 times 1 plus pi over 2, right? And that's the exact value of my approximation. It's an approximation already, so we don't need the exact value, so we'll plug that into our calculator and get an approximation value of around an area of 5.688356694. Obviously, you see I keep a lot of decimal places because it's already an approximation, so I want to keep it as accurate as possible, which is why I calculate the area approximation exactly, because now I am here, this decimal form is an approximation of an approximation, right? So I'm keeping lots of decimal values because I don't know what I have to do with the next. Okay, generally speaking, I said this before, 4 decimal values is good. So 5.6884, rounding this up, would be all you really would need in order to do calculations with it, unless I told you you needed more decimal values. Okay, and that is how we do a right-hand sum. Okay, so very straightforward. Figure out your delta x, your x values you need to plug into your function, and just plug them into your Riemann sum and add them all up. All right. See you guys later. Thanks.